avoid legal snags by telling people you're recording. Hey guys, I'm recording myself. Guess what? I'm the only person recording myself, so I guess that's okay. That's cool. So, 22, 23, and 24 we're supposed to skip, but I'm just gonna show you very quickly and then move right on up. So what this one is basically you have this dose, and then you have your loading dose, and so you have, I should change colors. So you have lovely, lovely little state, and that's what we saw in the previous one. But this patient, maybe they have they are the ultra fast ultra metabolizers for I guess let's just say this is like codeine. Oh, morphine. Morphine. Hey. So that would make sense. And so what these people are effectively doing is every 1.5 minutes they get to they get to add a little bump, and then it goes away. But they get to add another bump before it completely eliminates, because the half-life is 1.5 hours, so it keeps bumping up and keeps bumping up and keeps bumping up. So it kind of makes your steady state a little bit higher, and that's all this is trying to show. And we haven't gone over it, so I'm not going to go through it, because our prof already told us not to, because I'm very thankful. I don't feel like learning today. I feel like teaching you guys. I'm just joking. I'm doing this for myself. Alright, so we're in scenario 11, which he ran through in class, or the distance student TA did, and she's amazing. Alright, so for 25, we are trying to find the appropriate loading dose for an 84 kilogram patient who her heart rhythm is either tachycardic or fibrillation. Just her heart's beat crazy. So we give her a procainamide to control her heart rhythm, and so we have to give her an IV bolus loading dose, and target concentration we want to get to is 7.5 milliliters or milligrams per liter. So we're going to suggest a loading dose because we're the pharmacist at this hospital, and evidently we know what we're doing because we graduated pharmacokinetics, and we're A students, and this is basic stuff. We know how to do this. So 25. Like my pep talk? I do too. So our concentration steady state that we're trying to hit is 7.5 milligrams per liter. So the first thing that we need to do is to figure out our dose, which is we've got to find our volume of distribution. Well, thank God they gave us the 84 kilograms, because I don't feel like converting pounds to kilograms. So 84 kilograms times 2 liters per kilogram. I wonder if this patient has diabetes. I don't know. Does it matter? Not really. So this our volume of distribution is 168 liters. So we found our volume of distribution. So now we take the volume of distribution times our concentration steady state to find our dose. So 168 liters times 7.5 milligrams per liter equals a ton of drug, nearly 1 gram, or actually more than 1 gram. Yeah. Alright, so we found that we need a ton of drug to get this lady's heart under control. Yay, we're saving lives. Imaginary ones, but that doesn't matter. So now we need to find an appropriate infusion rate for this concentration that we want to achieve. So the concentration that we want to achieve, we need to find the infusion rate. This is an infusion rate. But we don't have a clearance yet. So we have to go find the clearance first, which clearance equals KE times volume of distribution. We just found volume of distribution over here. It's this thing. But we don't have KE. So we once again have to go find KE, which KE equals ln 2 over T 1/2. Did they give us T 1/2? Yes, they did, people. So KE equals ln of 2 over 2.5. And I did not calculate that out on my paper, so I'm going to do this right in front of you, like magic. So our KE is 0.2773. Alright. Then we're going to put it by our volume of distribution, because now we have our KE, so I'm going to just put it right there. And we have our volume of distribution up here, so, and that's in inverse hours. I don't know why I keep forgetting to label stuff. I guess it's just because I used to do this all the time in the lab, and I just knew I used a lot of Excel, so I just had everything already automatically label itself. So clearance is equal to 4658 liters per hour. Then we already said that we want our concentration steady state to be that. I'm sorry for the amount of stuff that's being poured right here in this small margin. So you multiply yes, you multiply these two, and you'll find that RO 349.35 milligrams an hour. Okay, I'm gonna page down. So that's our 26. All right, 27. Actually, I'm gonna use different color because I can hardly differentiate from between these. So this one, we are trying to find our steady state concentration, assuming the loading dose was 100 milligrams and the infusion rate was 5 milligrams. Really? Trick question. All right, so your steady state is this. The loading dose means nothing. It just helps you achieve that steady state faster. But this is actually what your steady state is. So we already know that our steady state is 5 milligrams per minute. But the issue is we don't want this minute. Absolutely do not. So when she did in class, she just multiplied it 60 minutes over an hour, and that equals 300 milligrams per hour. Yeah, go us. We know how to calculate. Alright, I'm gonna erase all that so you guys can actually read. Now I'm gonna change colors again. We're gonna go on to the next one. 28. I need some space. So I am gonna delete all this so that we have some space here. If you didn't catch it, just pause it, go back, pause the video right there, and you'll be able to copy it down all. But I'm writing as fast as I'm not writing that fast, so it should not be that much of a problem. And I already changed my colors, so cool. So now we are on Cool Purple 28. So this one is asking, I already jumped the gun. What is the concentration 4 hours after administration and initiation? So the way this one is going to be is C of T equals the concentration initial, which also equals D over B, and then multiplied by the elimination rate constant by the time plus, so this is all one thing, and then it's plus how much are we putting in, how much are we getting out. So rate times how much is degrading. Are we degrading? How much are we degrading? And how much is staying? All right. So that's the whole second half. Okay. So first thing, 4 hours after the administration learnings and initiation. So they're both at 4 hours. So in this one, the big T and the little t are the same. From the previous question, where it said the loading dose was 100 milligrams, and we already had the volume of distribution was 168 liters, and we already had the K elimination, which was 0.2773. So I'm going to start writing this out so that you guys can see the magic of science. Alright, times E negative 0.2773 times 4 hours. I like bubbles, I don't like brackets that much. I'm going to put this down here just because it's very bulky. Or at least the way I write it, it's super fat. Who's fat? This equation. Now, this becomes e to the 0 because in here, 4 minus 4 is 0, so this becomes e to the 0 becomes a 1. So we don't need that, that disappears. So, just explaining. So the first big bracket I got is 0.06475 when I put it into my calculator, and I add that to this second very large thing, which is 1.8930. I would stress that you keep those two separate when you're calculating, because I remember on an exam we had a very intricate one about the elimination rate of alcohol, and I screwed that one up, and I regret it to this day, and I still remember it because my professor thought I would get it, and she was very cross. I always went to my my professor's office hours because we like to be buddies and hang out. I like kinetics. I'm a nerd. What else is new? So now this one is the same thing except It's 8 and 4 hours. So which one's the big T? Big T is going to still be 4 hours. Little t is now going to be 8 hours. So what does that do to us? Well, we're going to use this same equation, so I'm not going to rewrite it, but I am going to start filling in stuff right now. Seven, 773 times 8. Because that's little t, if you guys remember, that's not big T. Alright, rate of infusion is 6.44 grams. Oh, did I do some? I think I did something wrong. Oh, did I? I may have jumped the gun. I didn't do something wrong. I may have jumped the gun, and that's why I'm looking at this. Okay, so our rate constant. Okay. All right, our rate constant is 3 milligrams per hour, and the other one is milligrams per liter, which is our CSS. All right, so I just scared myself. This is CSS, not RO over CL. That's why I'm like, because I didn't change it after I finished the equation. Because, well, I thought tonight I was the only one that was going to see these notes. But evidently people need help with, or, well, they don't need help. You guys just want to feel confident, which is cool. I'm cool with some cool cats. So because there's now a difference here, this is now exists. Yay, you exist. Okay. So now this whole entire section becomes 1.8930. Oh, ha! I'm an idiot. This is not the right one. I will put that back in. That is actually the one to over here. Because I'm misreading my notes. I should do the calculations with you guys. And then that becomes 1.9577. Concentration at that time is milligrams per liter. Okay, so for this one, because I bungled up a little bit and misread my notes, this one is 0.196 plus 4.3159, and they become 4.5119 milligram per liter. So, sorry, I didn't mean to give you guys a heart attack, make you think that you got it wrong, but no, you were in fact right. I'm just, I'm trying to rush through these so that I can go to sleep. And, well, and I'm also on like 1 hour of sleep. But we're gonna go on to, number 12 in a second, and I will stop recording this one.